find V minus, VA, and Vout in this configuration when we have some input voltages given the gain of this op-amp and the VD-on of these two diodes. The first step that we have to take is to identify the points before and after these diodes. So, before diode D2, the point is A. After the diode D2, the point is the output Vout. How about D1? Before D1 is this point, which is this point, which is the inverting input of the op-amp. I'm going to name it X for convenience. Step number 2. I draw my little table over here for D1 and D2, whether they are on or off, under which condition for which Vin, and how much will V minus, VA, and Vout be for that condition. And then, and only then, I go ahead and check into which of these categories these four values belong. Now, this is an advanced exercise, so pay very, very close attention so that you also develop this intuition. See that, well, if we start with both of these diodes being on, so both of these being a battery, let's say like this, well, if both of these two diodes were to be on, a current would have to flow like this, because the diode does not allow a current to flow backwards. So a current should have to flow like this, and then perhaps it would split into some of it here, but there should be another current flowing like this from here all the way to here, alright, like this. Then this current would have to flow upwards. If this current flows upwards, it has to flow inside here. If the current flows like this, the voltage here has to be higher than the voltage here or here. If the voltage here is higher than this voltage, it's impossible to have the conditions of both of these two diodes being on. Let me explain. For D1 to be on, Vx minus Va must be equal to 0.7. Alright, the VD-on of this diode. For D2 to be on, Va minus Vout, the voltage here minus the voltage here, that's why we identified this point, must be 0.7 also. That means, if I go ahead and add these two, I have that Vx minus Vout must be 1.4 volts, the voltage difference. Therefore, Vout cannot be higher than Vx for the currents to flow like this. Therefore, both of the diodes being on is an impossibility. So for no Vin, we have these two being on. It doesn't happen ever. I hope it is clear, and let's move now to the second case. Doesn't matter which one we do first. I'll choose to do this for teaching purposes. So let's say for both of the diodes being off, what would happen? Well, if both of them were off, both will be represented by open circuits. But now the first thing I notice is that I don't have a negative feedback over here, so this is very strange, but let's continue anyway. Now, the first thing I always do is write the conditions of the two diodes. So, D1 and D2 are off. That means what? That Vx minus Va must be less than 0.7. Also, Va minus Vout must be also less than 0.7. Now, there is the second golden rule of the op-amps, which is this condition for the outputs, and we are going to go ahead and replace V plus with 0, V minus with Vx, and we are going to have that Vx is equal to minus V out over A. Now, we have three different equations. Also, before I do anything, I notice something here. This V out is connected to this Vx. but no current flows really here or here. If no current flows, that means that Vout will be equal to Vx, because the resistor plays no role into lowering the voltage here. Alright? No current flows, this voltage is the same as this voltage. So I'll go ahead and write it. Vout is equal to Vx. But also notice that if no current flows over here, and since no current flows inside the input, the first golden rule of the op-amps, that means that also no current flows here, or from here to here. That means also that Vx is equal to Vin. Alright, very strange series of events here, but bear with me. Also, I made a mistake here. This is not Vout, this is Va. Let's not get confused. Vout is not the Vout of the op-amp in this configuration over here. Va is the Vout of the op-amp. Alright, now let me go in this equation and I will multiply everything with -1. You will see why. The sign of the inequality reverses, and we have that Vout minus Va must be more than -0.7. We also have that Vx minus Va is less than 0.7, but Vx is equal to Vout. Therefore, if I name this 1 and 2, we'll have the following. Alright, now I see that when Vout minus Va is less than 0.7 and more than -0.7, both of the diodes will be off and all of these things would hold true. Now, how much is Va and how much is Vout? Is this a useful expression? Well, Vout is equal to Vx and Vx is equal to Vin. Over here now, therefore, I can have Vin and see the conditions. But how about Va? Well, Va, I also gained this condition over here. Va will be equal to -8 times Vx. Therefore, this whole thing becomes the following. And now, if we do simple math, add these two, so it's 1 plus A times Vin, and then divide everything. 1 plus A is positive, so we won't change the inequalities, and we'll have eventually, which is equal to 0.028 with a minus. This tells me that when Vin is going to be between these two very small values, both diodes will be off, and Vx will be equal to Vin, Vout will be also equal to Vin, Va will be equal to 24 times Vin with a minus sign. Alright, we are ready to move, let's say, on this case where D1 is on and D2 is off. Now for that case, D1 is on, so it will be an battery. D2 is off, it will be represented by an open circuit. First things first, I notice that no current flows from here to here, so Vout will be equal to Vx, like before. Now, next step is to write the conditions. D1 is on, therefore Vx minus Va will be equal to 0.7. Remember, this is a battery. Now, D2 is off. That means Va minus Vout will be less than 0.7. Next, since I'm not sure what else I can do here, I'm going to take the second golden rule of the op-amps, which is the previous equation. How much is V plus? 0. How much is V minus? I'll write it Vx times again, just like before, nothing different. Now, I need to find the condition for the in, right, for the input. Let's see. If I were to find a condition somewhere, it would be here, on this, and in this case where D2 was to be off. Because see, Va minus Vout must be less than 0.7. So This guides me here. Now, can I write VA in relation to Vin somehow? Well, I can, due to this equation, I can say VA is something Vx, the closest thing I can get to Vin. Alright, how about Vout? Well, Vout is Vx, which must be less than 0.7, so let's write the equation here. So Vx must be more than this value over here, this negative value. Alright. At the same time, we have this condition over here, Vx minus Va. So Vx has to be 0.028. Now, it doesn't seem that we can do anything else over here, so we perhaps could have taken a KCL, let's say V in minus Vx over R is equal to the current that flows over here, but we would not get anything useful for now. So what I'm going to do when you reach this situation, because it happens, right? We are going to not write V in over here, but we are going to write everything else. Why? Because then we will go to the next case in which we will have a definite condition for V in, and then we can go ahead and supplement the condition over here for the other areas that have not been mentioned. So if for this is V in, let's say, more than 20, then the rest of the areas that were not covered here are going to fill up this case. So there must be some condition that produces this result. We don't know it yet. We cannot be sure from this. Okay, so let's move on. On to the third case where D1 is off and D2 is on. Well, if D1 is off, it will be an open circuit. If D2 is on, it will be a battery with these polarities. And now, of course, as always, the first thing that I'm going to do is to write the conditions for the two diodes. So for D1, Vx minus Va less than 0.7. For D2, Va minus Vout must be equal to 0.7. Now let's take the condition for all op-amps, which is the following. Va will be equal to V plus minus V minus minus Vx times A. Alright, now we can do something that we could not do before, which is to take a meaningful KCL on node X. V in minus Vx over R will be equal to Vx minus Vout over R. These resistances get cancelled out, and then we have an expression for V in, a very clear expression, which is 2Vx minus Vout. Now I need to express this inequality in terms of V in, so how much is Vout? 0.7 plus, sorry, it's Va minus 0.7, so this Vout gets replaced with Va minus 0.7. How much is Vx? Minus Va over A. So now we have an expression with Va and a number here. And we can go ahead and do some math. Alright, now I can go ahead in this inequality and replace Vx with Va over A with a minus. So Va will be more than minus 1.042. So VA must be more than 0.729. Now I can go ahead and replace this expression inside here very carefully, like approximately. Therefore, I have a very clean condition for Vin when Vin is less than 1.490. Well, in that case, VA will be given by this expression. Vout will be given by VA minus 0.7 from over here, right? And VA is given by Vin, so everything is relation to Vin. And how much is Vx? Very simply, VA over A times minus 1, of course. So everything is in relation to this Vin in over here, clearly. When Vin is less than 1.490 volts. Now that leaves us with the rest of the values that Vin can take, which is anything less than this value, 0.028. This up until this is covered. This up until this is also covered. But everything above Vin is not covered. Therefore, this would hold true for Vin more than 1.490. And now we are ready to see how much are these values. What if Vin is plus 1 volt? If Vin is plus 1 volt, we fall into this category, and then we simply solve these for this Vin to get these expressions. How about when Vin is plus 3 volts? If Vin is plus 3 volts, we fall into this category. We have constant values over here. How about when Vin is minus 1 volt? We fall into here. Again, we solve these equations, same as with minus 3. Right? We'll go ahead and solve these equations. I know that you can solve this. It's very easy, just replace this Vin value over here and do the math pretty simply. For more exercises like this, along with the solutions, if you like the way I teach, check out the link I have prepared for you in the description below. Also check out this playlist over here. Study well, take care, goodbye.